Thank you. Thank you, committee, for inviting me to this fourth edition of the Chemistry World Conference. And today I want to talk to you a little bit on the characterization of iridium-based catalyst for proton exchange membrane electrolysers. I'm from the Nelson Mandela University, and that is based in South Africa. New name of the city is Gouws, previously known as Port Elizabeth. This is our campus, just for interest sake. But more or less, we're going to talk about the reduction of platinum group metals. There's quite a drive these days to go to carbon emissions, net zero emissions by 2030, and by 2050, total carbon emissions, especially in refineries and also in energy. Now, we're looking at particular at electrocatalysis, use suitable descriptive metals, like, for example, at the moment, the catalyst for proton exchange is platinum on the cathode side and iridium on the anode side. We're looking at reducing that iridium. It is scarce. It is also very expensive, and we need to look at alternatives. And now the alternatives that we're looking at is going to be gold, looking at ruthenium, looking at titanium, nickel, cobalt, and manganese. It's important to look at these catalysts to find stability as well as longevity in the electrolysers. In this talk, we're going to a little bit talk about the characterization of bimetallic mixtures, in particular looking at XRD, XRF, SEM analysis, and also the transition electron microscope analysis. We're going to look at some electrophysical characterization that's more from a chemical point of view to see what is the behavior of this catalysis regarding cyclic voltammetry as well as linear scan voltammetry. And then we're going to look at later on the construction of a 1 kilowatt electrolyzer, what I'm currently busy with. So we're going to we can look at the chemistry, but we're also going to look at the process. Right, for those of you maybe not familiar with rainbow colors and schemes, just to highlight, hydrogen is classified in various colors of the rainbow. And obviously the main ones, what we don't want, is the gray and the brown. That is predominantly from fossil fuels and coal, and in particular South Africa and other places in the world as well. We are coal burning, especially for electricity and other processes. We need to move away from that. Obviously, there's carbon sequestration always through the blue, and then there's also other colors, like, for example, in Japan, using pink hydrogen from nuclear, and then turquoise, and then in particular from solar panels, yellow, and then, of course, natural occurring reserves they found of hydrogen, what is called white. We, in particular, utilizing green hydrogen, splitting of water through electricity, in particular using renewable energies. Right, hydrogen can be used in various forms. Obviously, that is to move away from carbon emissions, looking at energy, looking at the production of ammonia. Our previous speaker spoke a little bit on the Haber-Bosch process and water gas shift reaction. And all this can be utilized where you can add green hydrogen. So what we're looking at, okay, we're looking at this first stage, using renewable energies, splitting the water into the electrolyzer with hydrogen, and then that goes in and storage or industry processes, ammonia, methanol, and other processes, and then, of course, back into the grid. And then down to the commercialization of various processes or products. The straightforward chemistry. Overall chemical reaction is obviously the splitting of water into hydrogen and oxygen. There's the molecules, obviously the electrons, and then they combine over a fuel cell, so one can utilize both the mechanism as well as the combining the oxygen and hydrogen again for energy. Our main aim is industrial processes. So that we're looking a little bit on electrocatalysis. We're looking at and see what we can achieve through electrochemistry. How we do this is we're looking at iridium or metal chlorides, and we then add some nitrate to it, oxidize the chlorides into oxide, and making various alloys, mix it together, stirring, and making the dried powder or the catalyst mixture that is then being inked, preparation with isopropanol, and then of course dipped into a glossy carbon and then analyzed on the cyclophotometry. So once we have the cyclophotometry, we can now find out what is the EPA value, what is speciation on these metals, and what is needed. Right, we're going to go back a little bit later on cyclophotometry once again. What's important also to look at materials. Now, there's various techniques, as I mentioned right in the beginning, XRD, XRF, SEM analysis that need to be done. We need to look and see, is the alloying formation between the two metals before they go in as a catalyst, or are they separate? How do they behave? Now, there's various techniques that can be done, and we're going to look at specifically, going to just touch on XRF and XRD analysis for a couple of oxides. This work is reasonable new for us. We've probably been busy with this one for the last 2 years. I'm an MSc student, although I've been involved with this for quite some time, but particularly looking at these bimetallics and also trimetallics. Now, iridium ruthenium oxides, there's some nice mixtures that come through. Now we're looking at 50-50, 30-70, and 20-80. Although ruthenium is also a platinum group metal, it's considerably less expensive than compared to iridium, which is about 4 or 5 times more than that of ruthenium. So you can see that's nice alloying as formation here between the two metals. But when we're looking at iridium gold, unfortunately, we see much more crystallization between a gold and a ruthenium, and the iridium structures. And then also another very important one that we're now busy investigating and want to take further is on the iridium titanium. Now, titanium is also a local mining element from South Africa, and this will be reduced cost considerably if we can actually got some decent work on this, and that can actually be a game changer, I think. But in this case, you can look at the iridium titanium. There's some good binding there. There's some good alloying, a good distribution of metals, and this will be further investigated in due course. Obviously, I mentioned cyclophotometry, and iridium, we looked at decreasing the iridium content. Now, like I mentioned, that is 4 times more expensive than platinum. And in this specific case, we'll take the concentration of 2% right down to about 1.1%. Yes, you're losing quite a bit of activity, but consider 0.5%, we still have very good activity. This is good, because then we can see, okay, well, what can we add with the iridium that can work in the MEA conditions where it's very highly acidic? Because remember, this polysulfonic acid membranes, what they use is a sulfonic acid base, and the pH dropped down to 2 to 3 pH. So we need to have a catalyst that is going to be robust and not going to be corroded away with time and actually causing shorter durability conditions for these catalysts. On the iridium ruthenium oxide, we also have found some good activities, and there is some companies that actually now are taking this even further to commercialization stage. So we use this as a benchmark to actually look at our other catalysts that we want to develop and take it from there. Then we also have looked at some other collectors, because it's not just the catalyst, but also what you're using for collectors, titanium and stainless steel. And we found some good activity there. The Tafel slips also have shown considerably good regarding titanium and stainless steel. And although these are elementary knowledge on fuel cell and electrolyzers, we can now start building electrolyzers from there. And that is the next stage, and there's a lot of work being done globally in the industry also on this type of level, and taking it, and so that we can actually make this in a more commercial space. Linear voltammetry scan is also important, because as we can look at the activity and what type of potential we need to split that water, which is roughly about 1.24 volts, into correct volumes and look at the robustness of these catalysts. And like I said, iridium ruthenium and iridium gold is one that we have tested here on lithium voltammetry scans, whereas the other metals are still beyond the testing. But just to briefly here, we can already see that the gold is a little bit longer and need more time or more voltage before they start splitting the water. Where compared to iridium ruthenium, very good activity, and it shows very good comparison to that of iridium on its own. Then we also need to look at potentiometry. Now, this is a technique that has been utilized in industry and also for electrochemists to look at the durability. Obviously, it will be compared to if you put a cell on, connected to renewable energies, and you can look at your potential over time that need to be stable. And this was done in about 240 minutes. We will do it for longer. Unfortunately, one of the things in South Africa in the past was also load shedding, but we now basically counted. And we're putting in renewable energies to actually do long-term stability studies, and we'll start these studies to actually look at other metals and take it through and see what we can come up with as a good catalyst. And then we'll look at the manufacturing. Now, from the MEA perspective, and that was done on a surface, but we need to run small single MEAs. MEA is a membrane electrode assembly, and that is basically what we're looking at is the naphine, which will be coated with platinum on one side, iridium bimetallic mixtures on the anode side. We have the catalytic converter, the collectors in both side plates, and this is a typical one that we start off with. The reason why I've chosen this electrolyzer is that we can actually play around with it, plug and play. Most of the electrolyzers you get these days from commercial is all in already completed. But this one you can take apart and you can actually put in your own MEAs and actually play around the surface area. So that will be the next step. I've got a good master's student at the moment working on this and a couple of honor students. And the next thing is to take that through to a PhD level to look at the effectiveness and also collaboration with other investors and industry. How are we going to do this? One of our objectives, and we're currently busy with this, is a small demonstration unit. Now, like I said, the big thing here is to make sure the effectiveness of renewable energies before the water splitting, and the drive will be to actually get these done and take it through to the next process. And to do that, once this is finalized, we will then look at these various processes, and all these processes one can use green hydrogen. I mentioned ammonia. Ammonia is one of the big drivers because hydrogen can be transported effectively two ways, either by methanol, and that is like the water gas shift reaction, or by means of ammonia, the Haber-Bosch process. Effectively, then it can be cracked and you can get your hydrogen from there, and then that can be utilized in other industrial processes, and locally we're going to utilize in the methanation process, Fischer-Tropsch process, and that can be used for transport, heating, small applications, forklifts, and so forth. So that is the outline where we wanted to go, and by doing this, we will look at various electrocatalysis and so forth. So the main problem overcome is anode electrocatalysis, and that is, like I said, is a global problem because of the capex and the capital layout of these electrolyzers. So one need to look and see how effectively we can actually start reducing the iridium content, how we can add other metals to this. And I know there's a couple of institutes around the globe that actually looking at this and finding ways either away from platinum group metals to non-platinum group metals. But this is something to look at, because demand for hydrogen is very high at the moment, and it's one of the hot topics to drive, and there's quite a bit of value chains have been developed in the hydrogen space to reduce this carbon emissions. This project also aimed for the longer term to develop manufacturing of know-how and catalyst production, and MEA fabrications, and especially for our local industry here in South Africa, in the Eastern Cape area. And then to investigate a single MEA electrolyzer to study, determine the best suitable OER, oxygen evolution reactions. And then one objective also is to look at the small demonstration unit where we can actually now plug and play and produce in the hydrogen that can then go into industrial processes or even for water electrolyzers or energy. We have a couple of articles already on this, basically looking at various production and looking at the characterization predominantly, and then we want to take this now to the production stage with industrial partners and government. I just want to acknowledge the committee for inviting me for this virtual presentation today, as well as thank you to the students that have worked on this over a number of years, and for the Nelson Mandela University support, as well as support from our research funders, industrial funders, and the National Research Fund. Right, and that's why we slowly change the world as the university's slogan. And I thank you for your time and for listening to me at this conference. Thank you. Thank you, Chair.